Hello students and welcome to the 58th lecture on particle physics. And recall, in the last lecture we were talking about Lorentz transformation of position and velocity. What I was telling you, that if you have two frame of references S and S prime, both are initial frame of references, and S prime is moving with a velocity v towards the x direction, and if some event is taking place in space, then that point in space will be the coordinates for that. Say for S prime is x prime, y prime, z prime and t prime, and for S is x, y, z and t. Then these two coordinates x, y, z, t and x prime, y prime, z prime and t prime are related via the Lorentz transformation. This was for the space part. Then we talked about that using this we can obtain the relationship with the velocity part, and that was ux prime was dx prime by dt prime, and from here we saw that ux prime is ux minus v upon 1 minus v ux by c square, or ux is ux prime plus v upon 1 plus v ux prime by c square. This was the point where we stopped. The important catch from here is, for example, if ux prime is say c, that means in frame S prime, the velocity of the particle which has been measured is if the speed of light, then in x it will be, you see, just I am putting it here, c plus v upon 1 plus vc by c square, and that is nothing but c. Therefore, the speed of light measured in the frame S, or the particle's speed measured in the frame S, if the particle in S prime was found to be moving with a speed of light, here also it will move with the speed of light. That one has to consider. And then if I take ux prime is equal to v is equal to 0.5 c, for example, then what you will realize that 0.5 c plus 0.5 c will give you c, and then this is 1 plus 0.5 into 0.5, 0.25 c square by c square. Therefore, this is c upon 1.25. Therefore, what you are finding out, that there is a 20% reduction in the speed if you are taking ux prime is equal to v is equal to 0.5 c. But if you consider the Lorentz Galilean transformation instead of Lorentz transformation, then this value will, when you want, simply add it up, and then this will be just c, which has not been found to be true. Exactly the value is that this value get reduced by 20%, and this is experimentally confirmed. Now, once we have the position transformation, once we have the velocity transformation, and this I am again going to use when we will talk about the laboratory frame and the center of mass frame. Therefore, what I am telling you, that ux, uy and uz, or equivalently ux prime, uy prime, uz prime, they are related to ux, uy and uz by this relation. This is a simple relation where v is the speed with which S prime is moving along the x direction, or x and x prime both are along the same direction. Okay, that is an important catch. Then we are moving to understand what will be the energy and momenta in these two frames, and how energy and momenta of one frame would be related to energy and momenta in the other frame. And if one frame is laboratory frame and another is center of mass frame, then we will see that the relation becomes very easy to understand. Therefore, what I am talking about the energy and momentum of the particle in the inertial frames S and S prime. Now, if you notice, recall from the basics of special theory of relativity, in S, the energy will be simply gamma u m naught c square. Px will be gamma u m naught ux. Py will be gamma u m naught uy. And Pz will be gamma u m naught uz. If I ask what is gamma u is nothing but 1 over square root 1 minus u square by c square. Now similarly, if I want to express this in S prime frame, then simply E prime will be gamma u prime m naught c square. Px prime will be gamma u prime m naught ux prime, and so on. And that means gamma u prime is 1 over 1 minus u prime square by c square. But this was not our task. Our task is to relate the quantities, these kinematical quantities, in these two frame of references. And that means we will try to express gamma u prime first in terms of, say, gamma u. And then we will say that, okay, if you gamma u prime is in terms of gamma u, that means directly you can see that how E prime will be related to E, or how Px prime will be related to Px. And therefore, mind it, these transformation, velocity transformation, and this guy, gamma u and gamma u prime, these are the important quantities to us. Therefore, gamma u prime, this is 1 over 1 minus u prime square by c square, and that is equal to 1 over 1 minus ux prime square plus uy prime square plus uz prime square by c square. And that means what I am supposed to evaluate, if I evaluate 1 minus ux prime square by c square and minus uy prime square by c square and minus uz prime square by c square, then I will be able to, that means, evaluate the quantities which are there in the bracket. And now you see ux prime, we know from here, ux minus v upon 1 minus v ux by c square. Therefore, I am going to put back here, this is 1 minus ux minus v whole square upon c square 1 minus v ux by c square whole square. And this is simple algebra. Similarly, this will be uy prime square by c square, and if you want to write uy prime square by c square, you will have this quantity as uy by gamma v c 1 minus v ux by c square whole square with a minus sign outside. Similarly here, minus uz by gamma v c 1 minus v ux by c square whole square. And when you will solve this, this will turn out to be 1 minus ux square by c square times 1 minus v square by c square upon 1 minus v ux by c square whole square. Therefore, what you are noticing, that everywhere you have this term which is common, and then you are going to put it together to get 1 minus ux prime square plus uy prime square plus uz prime square by c square. And when you do that, then that means 1 minus u prime square by c square is equal to 1 minus u square by c square 1 minus v square by c square upon 1 minus v ux by c square whole square. And this is nothing but, remember, gamma u was 1 over square root 1 minus u square by c square, or gamma v was 1 over square root 1 minus v square by c square. Following the same analogy, we can write it as 1 over, this is 1 minus, this is the square root. Therefore, we have to take the square root of this, and you see gamma u will come in the denominator, gamma v will come in the denominator, and then we will have 1 minus v ux by c square. And therefore, E prime that we talk about, this is equal to gamma u prime m naught c square, and this will become equal to gamma u, gamma v, 1 minus v ux by c square times m naught c square. Therefore, you notice you are writing E prime as gamma u, gamma v times 1 minus v ux by c square m naught c square. And remember that this guy along with this is nothing but, we can write gamma u m naught c square minus gamma u vux by c square m naught c square, and this is equal to gamma v, this is nothing but E minus v px. Therefore, E prime is gamma v E minus v px. Similarly, we can evaluate what will be px prime. Px prime will turn out to be gamma times px minus ve by c square, and py prime will turn out to be equal to py, and pz prime will turn out to be equal to pz. You know E and px, you will be able to get E prime, that means energy and x component of momenta in frame S. You will be able to tell what will be the energy in frame S prime of that particle, or if you know the momentum and energy in frame S, you will be able to tell what will be the momenta of the particle in frame S prime. And not only for x component, similarly you can do for the y component, as well as you can do it for the z component. So therefore, that is an important catch, that not if we have a lab frame and center of mass frame, it is not necessary to know all the kinematical quantities individually for both the frames. But if you know it for the one frame, that means yesterday we spoke about, if I know energy of the projectile and the lab scattering angle, I will be able to tell at what was the energy of the outgoing particle 3, at what angle the fourth particle was moving out, and what was the energy of that fourth particle. Therefore, we were knowing the energy, you know, then that means you will be able to tell the momentum of the particle P4 prime. Therefore, the important point is that you know P4 prime, you know E4 prime, you know phi, and moreover, we are talking about scattering where the projectile is coming with certain energy and momentum. This is taking place in two-dimensional space. Therefore, from here you can also be able to tell what will be the momentum and for P3, and what will not only magnitude but also the momentum for P3 and P4 prime. And that is the beauty, that if I know the kinematical quantities in lab frame and center of mass frame, I can relate them. And that means what I am telling you, that if I have, say this is x, this is y, this was the target, this was the projectile 1, this is the target 2, scattering is taking place and particle 3 is moving out. This is making an angle theta L. Then if I know theta L and this quantity is E3 P3, this quantity is E2 is equal to M2 because target was at rest and 3 momenta was 0. This particle has energy as well as momentum. And what is its energy? This is square root P1 square plus M1 square. Therefore, I know its energy, I know its momentum, I know that the particle 2 was at rest. Then what I had told you, we will, if we know theta L, we will be able to calculate E3 and we will be able to calculate P3 in this two-dimensional plane. And similarly here, the particle which is going along this direction at an angle phi, this we are calling by the name the recoil particle, we will be able to also tell what will be that angle. Okay, that is the important point while doing transformation from one frame to another frame. Therefore, let me erase it, and just we are writing the case where we are considering transformation of the angle. Therefore, when we are talking about the transformation of the angle, we have to keep in mind that first we have the energy. The energy is E equal to mc square, and that is equal to m naught c square upon square root 1 minus v square by c square. Total energy, that means depends upon the speed of the particle, and the momentum is p is equal to mv, and that is equal to m naught v upon square root 1 minus v square by c square. Now, as you can notice that if I plot mass on the y-axis and speed on the x-axis, we see that this graph grows like this. Now, if E is equal to mc square and that is equal to m naught c square upon square root 1 minus v square by c square, then equivalently E square will be m naught m squared c4, and m square we are writing in terms of the rest mass of the particle, and that will be m naught squared c4 upon 1 minus v squared c square, and this will result as E equal to m naught squared c4 plus p squared c square square root. Now, there can be two possibilities. If the momentum of the particle is much smaller than, or the energy of the kinetic energy of the particle is much smaller than the rest mass energy, then what does that mean? If p is very small, I can write it as m naught c square, I can take common from here, and then this will be 1 plus p square c square upon m naught squared c4, and c square with c4 will get a c square in the denominator. Therefore, this is m naught c square upon 1 plus p square upon m naught squared c square. Since this quantity is much smaller than this, we can expand it and retain only the up to second term. We will get a term that will be what we write in the non-relativistic case. The rest mass energy plus the kinetic energy of the particle is the total energy. Now, if this guy is going to dominate, then E is simply Pc. That means if P is going to be very large, then E is equal to Pc. The other important point is that energy is you are giving us m naught squared c4. This is a constant quantity, and therefore E square minus P squared c square will be the same as E prime square minus c square P prime square. This is an important relation which one has to understand, that though energy and momentum E and P measured in frame S and E prime and P prime measured in frame S prime, this quantity E square minus P square C square, this will be independent of what inertial frame you are talking about. This will be a constant. Therefore, this is what we have talked about: energy, we have talked about momenta, and now we are going to talk about the transformation of the scattering angle. And that means I am going to talk about theta lab and center of mass angle, right, for example, I write it like theta c. Therefore, theta lab is the lab scattering angle, theta cm is the center of mass scattering angle. The question is whether if I know theta lab, then would I be able to tell what will be theta cm? As I have told you that if I am performing an experiment at, say, for example, if I have 1 plus 2 scattering and we have 3 plus 4 as the final states, then if we have the common center of mass energy for lab frame as well as center of mass frame, and I have put a detector here at an angle theta lab, say 15 degrees and 20 degrees, and I have observed some event here, then since the cross section is a Lorentz invariant quantity, it does not depend upon the what frame you are talking about. Therefore, if I will keep this center of mass energy to be the same, then at what angle, that will be the equivalent center of mass angle where I will put the detector and I will get the same number of events. Now that means equivalently you can say that the point where you are getting the same number of events, at that will be the angle that corresponds to equivalent angle in the laboratory frame. That means if I know theta cm, I will be able to tell theta lab or vice versa. Therefore, the important point is that when we are talking about the lab frame and the center of mass frame, then if you recall, my A plus B PA is, say, it has components, particle is moving along the x direction also only, therefore the momentum is only along the x direction. PB, particle B in the laboratory frame is at rest, therefore when it is at rest all these components will be 0. EA will be the energy of the incoming particle, energy of the projectile. EB will be the mass of the target particle, mass of the particle B, and this mass, the particle is at rest. Now A plus B scattering is taking place and we are observing, say, particle 1 in the final state. And as we know, if we are observing 1, then we will be able to describe everything about 2, or if we are observing 2, then we will be able to describe everything about 1. Therefore, what we are talking about, the momentum of the outgoing particle, this is P1 cos theta L, P1 sin theta L, two-dimensional plane only, and this will be 0. Now the point is how to relate the lab quantities and the center of mass quantities. We have said that first we have to find out at what velocity the frame S prime is moving with S. That means first we will like to know what is V. That means first we will like to evaluate gamma V. Once we know gamma V, we will be able to tell what will be the corresponding quantity in the center of mass frame. Therefore, in the center of mass frame, if you recall from the previous expression, this PA prime, because in center of mass frame, both the particles will come from the opposite direction. And therefore, here we are talking about PA prime. Remember our expression, this was gamma V PL minus VL by C square. We have PL minus VL by C square, and PB prime, this will be minus MT V gamma V. Why? Because this component for B, the momentum component, is 0. Therefore, here only we are getting a component, and since energy of the particle is its rest mass, therefore we are getting minus MTV gamma V. See, E is MT C square, and that is why C square with C square has got cancelled out. We have PA prime and PB prime. That means momentum of the particle in frame A and the momentum of the particle in B. And now our first task is to get what will be the value of gamma V. And for that, in the center of mass frame, we know that these two particles are approaching from exactly opposite direction. Therefore, PA prime plus PB prime is 0, as we have discussed yesterday, and therefore PA prime is equal to minus Pb prime. Putting those values, you have gamma V PL minus VEL by C square. This is equal to MT V gamma V. And therefore, you can write your PL as equal to VEL by C square plus MT. That means what is your V is PL by EL by C square plus MT. Do you know this value? And if you know this value, that means you know gamma V. That was 1 minus V square by C square. And therefore, Px prime, if you recall, this will be gamma V P1 cos theta L minus VE by E1 by C square. Py prime will be equal to P1 sin theta L and Pz prime will be equal to 0. And from here, just what is your P1 prime, recall? From the two-dimensional plane, this will be P1 cos theta C, this will be P1 sin theta C, and the third component will be 0. Therefore, notice that you are knowing P1 cos theta C, you are knowing P1 sin theta C, and here you are talking about P1 x prime, P1 y prime, and P1 z prime. That means just you have to put these values here. You know that you have P1 prime as P1 cosine theta, P1 prime cosine theta C, P1 prime sin theta C, and 0. You are actually comparing these two values, and these two values are implying that you understand the quantities in lab frame, you understand the quantities in the center of mass frame. That means if I define tan theta C, this is equal to P1 prime upon P1 x prime. This will be equal to simply 1 over gamma V P1 sin theta L upon P1 cos theta L minus VE by C square. Therefore, notice that the quantities which we know in laboratory frame, we have put it here. We have 1 over gamma V. We are able to tell what will be the corresponding center of mass angle. This angle is known to us. Therefore, the important point is just through Lorentz transformation, simple Lorentz transformation, you will be able to tell about the center mass angle, laboratory angle, center of mass energy, laboratory energy, and all that. This is all about the kinematics, and then in the next turn, we shall talk about the accelerators, and in the last turn, we shall talk about the detectors. Let us stop here. Thank you very much.